Wang from Institute of Physics, Chinese Academy of Science. So now he is going to tell us about canonical transformation, neural canonical transformation for M star of two-dimensional electron gas. So Ray, please.
Okay, so thanks a lot for the introduction, and it's my great pleasure to be invited to this workshop to catch up with so many familiar faces. So I should also admit that this is not going to be closely related to tensor networks, at least for now. So probably through the whole talk, I'm only going to mention tensor network in the very end. But nevertheless, let's start it. A great success of condensed matter physics was actually the explanation of insulators, metal, and semiconductors. However, if you think it over or think more carefully, so it might not be that obvious why metal is metal. For example, let's take the simplest model for metal, the uniform electron gas. Let's take into account of the Coulomb repulsive interaction on top of the kinetic energy. So in this model Hamiltonian, there is actually only one tuning parameter, that is IS, the distance, average distance between electrons. So naturally, there are several regimes. Suppose this is a dense system, IS is much smaller than 1. Then because of the kinetic energy is inverse proportional to IS square, the kinetic energy dominates. In the opposite limit, if this is a very dilute system, Coulomb repulsive interaction dominance, that's where you had Wigner crystal and so on. But if you look at periodic table and look at the typical RS value for those metals, you are going to see that their average electron distance lives in a non-perturbative range compared to 1. Therefore, compared to the kinetic energy, the interaction energy is not negligible. Therefore, it's not that obvious those materials, they behave like a metal or non-interdicting fermion systems. So this puzzle was resolved by Landau Fermi liquid theory. So the essence was that even though the Coulomb repulsive interaction is as large as the Fermi energy, but if you only consider low temperature limit, where temperature is much smaller than the Fermi energy, then the interesting physics actually happens around the Fermi surface. So the scattering process due to the Coulomb repulsive interaction is strongly constrained. Therefore, for those actually strongly interacting systems, you can still label their low energy excitations, use the same quantum number as a non-interacting ideal Fermi gas. So for each of those excitations, you can think of them as something called a quasi-particle. They carry the same spin and same charge as a bare electron, but they have a different effective mass. So this is the topic of this talk. So actually in Landau Fermi liquid theory, only why a few parameters, including the effective mass, you can predict a large number of physical properties, including density of state, entropy, specific heat, susceptibility, and so on. However, despite of many years of study, this, I would say, fundamental constant for electron gases was still controversial. For example, this was an old result from Harding's paper more than 50 years ago. You see, these are some kind of perturbative analytical calculations for the effective mass versus that density parameter RS. So you see those curves, they differ a lot. And that was from a very recent diffusion quantum Monte calculation where they add a new line on this plot. But this still differs from another quite recent calculations by variational diagrammatic Monte calculations. So even though this was the latest result, I wouldn't say the puzzle was resolved. So this was for 3D electron gas. So you can view this as a kind of a academic question because in actual crystal, there was nuclear and so on. However, the effective mass was not an academic question for two-dimensional electron gas because people can actually prepare those things in the laboratory and they can tune their density. However, in those experiments, the measured effective mass also differs a lot, even qualitatively. Some experiments report enhanced effective mass. The other experiment report suppression of the effective mass. That suppression means that it's smaller than the bare electron mass. So there was actually a lot of complications due to the experimental situation, like the thickness, the value degree of freedom, or spin-orbit decoupling, and so on. So coming back to the theoretical prediction, for two-dimensional electron gas with Coulomb repulsive interaction, people even get very different prediction with the same kind of numerical method. So this is a plot from the textbook written by Martin, Renning, and Sepley. So people were using the same kind of variational or diffusion Monte Carlo to compute the excited state energies of the model and extract effective mass. However, there are some ambiguities in the kind of data processing process. Basically, it's not that clear how to extract the effective mass signal from the excited state energies in a finite simulation set. So that's why people get different predictions. So you see, this was not something that you can easily resolve within the numerical method itself. So it's not like if you just use a lot of more computing time or trying to improve the fixed node approximation, this is going to solve. So it's not that straightforward. So the routine we try to follow in this talk is from a thermodynamic measurement. So basically, the Landau Fermi liquid theory tells us that in the low temperature limit, the thermal entropy of the system is linearly proportional to the temperature, and the per factor depends on the effective mass. So that means, suppose you can compute the thermal entropy of your interacting fermionic system, the ratio of an interacting system over a non-interacting system, the entropy ratio, actually gives the effective mass ratio. So this is the basic idea. So what was needed was a numerical method that works at a sufficiently low temperature and predicts the entropy. That's it. However, this was actually a quite demanding task. That was because low temperature calculations for those two-dimensional interacting fermion systems was challenging. And even if that was possible with certain approximated method, usually entropy was not an easy observable. For example, for Monte Carlo calculation, so they can predict ordinary observables, but usually not entropy, because this is related to free energy. I think this is mainly because of these two reasons. So even though it's quite straightforward to say that there is a connection between effective mass and thermal observable, it's not carried out in the literature until very recently. So the way we try to solve interacting fermion problems at low temperature is via the variational free energy calculation. So this is the basic principle for thermal quantum many-body systems, meaning that you can set up such a variational objective function, that's an entropy, that's an expected energy. And for a physical variational density matrix, you can show that the variational free energy is greater than the actual free energy. The equality holds only when the variational density matrix matches the physical one. So this means, suppose you can set up the right variational space, meaning that the density matrix is a normalized positive definite and Hermitian matrices. And also for fermions, it should be permutation antisymmetric if you switch the position of the electrons. Then if you carry out variational calculation in such a space, you can actually approach to the true variational, true free energy. So that's the basic principle. And then the task is how to represent such a continuous space electron variational density matrix. So it satisfies those physical constraints. And so the whole thing is computable or optimizable. So there's a kind of straightforward idea about setting up a physical density matrix. That is, we just write the density matrix on top of a set of orthonormal bases. So here, psi k is a orthonormal many electron wave functions. And we have many of those wave functions indicated by the quantum number k. K is the momentum of all those electrons. And then we form a mixture on those bases. And P of k is a Boltzmann distribution, which is normalized. So formally, such a variational density matrix satisfies all the physical constraints. But then the question is how to actually parameterize such a orthonormal basis of many electrons, and how to parameterize such a normalized Boltzmann weight of electron momentum. So you see there are so many question marks because neither of those things is easy task. So the outcome, so the upshot of this talk is actually that those things is now possible with generative machine learning techniques with certain physical considerations. So let me first explain a little bit about what is a generative machine learning. Then we go to technical details about how to represent such a probability and many-body basis electron wave functions. So first of all, for those of you who heard a lot about machine learning, so very often people were talking about the so-called discriminative learning. This was like teaching a child to recognize imaging or recognize the character. So mathematically, this means to fit a function, or like to predict the conditional probability where y is like the character, x is like pixel values. However, generative learning is dealing with entirely different kind of task. So it's more like teaching a child to write new characters from all the characters he had learned. So mathematically, that means the goal is to model higher dimensional joint probability distribution so that later you can sample from such a probability distribution. So this is generative learning. So this has a closer relationship to what we want to achieve here. So within machine learning, people actually invented a large number of so-called generative models to model high dimensional probability of realistic data, like imaging, characters, sentences, and so on. So actually 3 years ago in Kobe, I was talking about tensor network as a kind of generative model. But here in this talk, we are going to make use of some of the existing generative models to solve actual physical problems. So before going to the details, there is also a kind of basic principles we need to know a bit to tell the difference between the basic setup in machine learning and in physics. Because in machine learning, very often, so for generative learning, so what was known was samples, like a data set of images and so on. And what was unknown was a generating distribution, because people assume those images were collected from nature with an unknown generating probability distribution. And there, the task was to learn from such data a model probability distribution So later you can generate more samples from this distribution. That's a task there. While in physics, usually what we had is the energy function, or let's say Hamiltonian. That's an analytical formula. And what was unknown was the Boltzmann distribution, the samples from Boltzmann distribution, or let's say the physical observables, or like partition function, which is a normalization factor of that Boltzmann distribution. Therefore, for those tasks, so typically what people need to do was to perform an variational calculation. So I call this learn from Hamiltonian, but because what was known was the Hamiltonian function. But the goal was to get an approximated variational distribution that mimics the Boltzmann distribution of that Hamiltonian. So the objective function is slightly different. But nevertheless, for both of calculations, we can see the central kind of a topic was how to represent the joint probability of pixels or joint probability of, let's say, this magnet or electronic degree freedoms. So those are the generative models that we are going to make use. So in particular, for those electron wave function example, I'm going to, for the electron density matrix example, I'm going to make use of two kinds of generative models. One is called normalizing flow. So that's an example from OpenAI's GLOW model. You see it does interpolation between neutral human faces. Another model is called the autoregression model. So you see that's another typical example called a WaveNet from DeepMind. It generates speech signal in a sequential way. So we are going to use those two models to model the wave function and the Boltzmann weight on top of this mixture, respectively. So let's go into the details. First of all, for the many-body orthonormal basis, it's psi k. So we are going to write it down in this form. So basically, in the coordinate representation, so this capital R is a collection of electron coordinates. So I'm going to map the electron coordinate to another set of quasi-particle coordinate. I call zeta, this yellow thing. And for the quasi-particle coordinate, I'm going to write its wave function as a Slater determinant of plane wave functions. Then I multiply the Jacobian of the transformation to the Slater determinant. So in this way, I set up a many-body wave function for the electrons. So let's check two things. So first of all, such an expression ensures the orthonormal properties for the electronic wave function because there is a square root of the Jacobian term. Second of all, psi of R is indeed a many-body wave function because even though the dependence on zeta was simple, but because zeta was kind of a nonlinear, quite complex function of R, so this can contain correlation effect. And on top of that, there is a Jacobian. So you can even view this as some certain kind of gestural factor multiplied to the determinant. So because this is also normal wave function, so intuitively you can understand the transformation carried out between the electron coordinate and quasi-particle coordinate, a certain kind of many-body unitary transformations. So initially, I had a non-iterating quasi-particle wave function. Then I perform a unitary transformation to it. So I get parametrized many-body, many-electron wave function. So this is what's happening. Because it's a unitary transformation, those state remains also normal. So the key of this parametrization is actually this bijective mapping between two sets of coordinates implemented by a neural network. This thing is called normalizing flow. Here is a kind of a Pullman's introduction to normalizing flow, because in machine learning, normalizing flow was a way to model probability distributions. You can easily understand what's going on, why this formula. So basically, normalizing flow is a multi-dimensional change of variable. So because of this additional Jacobian term, you can modify the so-called base distribution towards something interesting. So this formula even plays an interesting role in a one-dimensional neural network. You see why this nonlinear transformation, you can map Gaussian distribution to a bimodular transformation. And using this idea, in physics, for example, you can set up normalizing flow to transform physical Boltzmann distribution of molecules or magnets or coupled oscillators. So you can get decoupled degree of freedom where their distribution is more like a normal distribution. By stacking those things, you can carry out normalizing group kind of transformation, or you can also try to identify isolated slow modes if this was the transformation in phase space. That's related work. And nowadays, normalizing flow actually finds many applications in different branches of physics. So in case you are interested, please check those papers. So coming back to our application. So we use normalizing flow to map between electron coordinate and quasi-particle coordinate. So because those are fermionic coordinates, so we need to put additional constraint to the normalizing flow, because you see, if you swap the electron coordinate, you need to make sure you also got the same permutation for the quasi-particles. Because they are all fermionic degree of freedoms, you need to ensure this permutation antisymmetric. So this actually means the two operations, like the transformation and the permutation or the symmetry action, they permute or they commute with each other. So this property is called the equivariant property. And this is actually one of the central topics in designing those kind of neural networks. We use one kind of equivariant neural networks from the literature for the mapping between electron and quasi-particle coordinate. So to make the whole thing more concrete, we can look at one example. So this is actually Feynman's backflow transformation. So Feynman was using this transformation to deal with helium atoms. So essentially the idea was atoms flow in an interacting environment. So you can dress its environment with a particle to define a quasi-particle coordinate by this equation. So now, if you look at this equation, why a machine learning angle, you see, first of all, if you translate those bare atom coordinate a little bit, the quasi-particle coordinates also get translated by the same amount. This means, indeed, Feynman's backflow is an equivariant flow. By the way, so this equation also had the structure that you add certain kind of a correction to the back coordinate to get the quasi-particle coordinate. So in a machine learning language, so this is called the residual network because there's a kind of a skip connection. So in a modern language, modern machine learning language, this is one instance of equivariant residual flow. And the other thing is, in Feynman's time, they only need to use this transformation in a single pure state. So you won't care about the Jacobian. But nowadays, to make this coordinate transformation a unitary transformation, we need to track the Jacobian. But this Jacobian is easily computable with modern machine learning techniques. So another thing was that in the philosophy of deep learning, you can actually compose such a transformation into a deep neural network, deep structure, right? This is the word deep, where the word deep comes from. So interesting observation was that actually such a structure of composed residual block actually mimics the OLS integration of an ordinary differential equation. So you can actually view the transformation from quasi-particle coordinate to the electron coordinate as certain kind of integration of continuous dynamics. So this is actually quite interesting observation, allows you to continuously track the coordinates of your electrons all the way from non-acting limit to the strong acting limit to make this continuous moving electron cloud. So this was for the many-body wave function part. So next we move on to the probability distribution. So remember, this is a normalized probability distribution to the electron quantum number, those momentum K. So again, this is a high dimensional object because you have n electrons. So this capital K contains a set of electron momentum, single particle momentum. So to model that, we use autoregressive network. So basically it means you write down the joint probability of electron momentum as a product of a set of conditional probabilities. So an analog to, actually this is also the origin of such a model. So in a language processing, quick brown fox jumps. So basically to sample the word jumps, you compute the conditional probability of that word conditioned on all the words that already appeared. So because each factor, the conditional probability is easily normalizable because you just normalize the whole thing through your whole vocabulary because you have a limited amount of vocabulary. So translating this back to the electron system, the particle number here is the length of this sentence. And the possible allowed momentum in the reciprocal space is the vocabulary that you are allowed to sample from. Again, there's only one twist. That is, those momentums, those atoms, these electrons, they are fermions. So that means we are modeling a set of momentum. There should be no repetition, and also order does not matter. Therefore, you need to modify those autoregressive models a little bit to make sure it's a set. So once you've achieved that, combining these two things together, you finally get a model for a physical density matrix for electrons. So you see, this is really a combinatorically large number of terms. You see, even for 13 electrons in such a circle, the total number of possibilities in that sum was like 10 to the 11. However, why this autoregressive model, you can model all the terms, right, and sample directly from them. And on top of that, because this is also normal, you can directly estimate the entropy of such a density matrix, while the entropy of that probabilistic model. So in this way, you can carry out the variational free energy calculation for this density matrix. So that's the basic setup. So we call it neural canonical transformations. So there is a momentum distribution, then there is like the adiabatic continued. So Anderson called this adiabatic continuity, where you continuously drive the quasi-particle coordinate towards the electron coordinate here via flow. Then you have an ensemble of unitarily transformed state that models your density matrix. So you just, to minimize the free energy, just tune the initial distribution together with the transformation. So this is how you minimize the free energy. So there are two limiting cases of the framework. One is the simplest case. Suppose I'm at ground state, then I can set the probability distribution to 1 for one particular closed shell configuration. Then this is the optimization for a single pure state. This is reduced to the familiar variational Monte Carlo calculations. Another limiting case is suppose this is non-intending fermions. If you drop the Coulomb repulsive interaction, then I need to set the flow to an identical mapping because I do not need to talk about the quasi-particles because those particles are my degree of freedom. Then the question was like classical stat map problem. You need to distribute your momentum within a momentum cutoff. But since this is a canonical ensemble, you conserve number of particles to minimize such a variational free energy. So those two are the limiting cases where you can cross-check with existing results or analytical results and so on. But the actual interesting setup was somewhere in between, where you need to have this nested sampling. So the inner layer of the sampling was from the Born rule of the wave function. The outer loop of the sampling was for the Boltzmann distribution of this good quantum number. Then you joint train those distributions to minimize free energy. That's it. Okay, now move on to the result. First of all, some benchmarks to existing data. In three-dimensional calculation, if Rs is sufficiently large, meaning if the electrons are sufficiently isolated, path integral Monte Carlo with restricted path is trustworthy. So in this case, you see the variational calculation nicely reproduce Eason-Brown's calculation for in 3D with 33 electrons. So again, for ground state, there are so many variational calculations, or even diffusion Monte Carlo calculations. This was comparison with Tanaka and separately with Slater-Jastrow variational calculations. So we get even lower energy. That was because I'm having a neural network instead of a simple Slater-Jastrow. So then move on to the interesting case with interaction together with temperature. So this is the evolution of the entropy per particle with the training. So you see the starting point is the ideal gas entropy. And once I start to optimize the whole thing, the entropy goes down. And as I said, the ratio of this plateau value of entropy compared to the initial value actually gives me the signal, effect on mass. So this is telling me I'm getting suppressed effect on mass when the Rs, when the density parameter increases. And if you redo this calculation for a set of electron numbers, you get this plot. And here I'm comparing with certain existing diffusion Monte Carlo calculation for excited state, where they even extrapolated to thermodynamic limit. So from this plot, we conclude that we observed even more pronounced suppression of effective mass due to interaction than previous predictions. So the suppression is it's quite pronounced in the strong coupling low density regime. And this should be checked with a new calculation or new experiment. So by the way, if Rs is very small, then there is the analytical perturbative theory in the green color, but you can only trust it for sufficiently small Rs. It looks like it's consistent with our data. So what was the experiment situation? So there was actually certain experiment measurement from quantum oscillations, but you see those things, they actually spread quite widely depending on the sample. And also I believe those crying color and those colors, they are actually the same set of data. But in the literature, people mark their Rs value very differently. This is like to 20, this was to 10. So I'm not sure which one to trust. So for those kind of experiment data, it was not that conclusive to say, to tell the difference between existing calculations. That was ended and more recent two-dimensional electron gas measurement, where they directly measure entropy via this Maxwell relation. So it would be extremely interesting to directly compare to their data, because they actually measure electronic entropy while modulation of temperature. So looking forward, so I'm presenting to you some physical results of a new method. And I believe this method had a bright future for AB initial study of quantum systems at a finite temperature, where it covers lots of important domains where existing Monte Carlo method found quite difficult. And why now? That's a basic question you can always ask for many of the new methods. Why now is the time? I believe the fundamental principle to study finite temperature quantum system is a variational free energy. However, this was underexploited for many years, mostly because of that entropy term in the variational free energy calculation was intractable. So this was actually, I would say, now solved with integration of generation machine learning, because in machine learning, people care about those intractable partition function cases. For normalizing flow, for autoregressive models, people can indeed compute its partition function. And also they have sufficient amount of expressibility to model rather complex phenomena. So that's why I think this actually opens a new way to study such problems. So there was certain very typical questions I got for those kind of machine learning talks. In case that's also your question, let me just clarify about it. So for this calculation, this is a variational calculation. There is no training data. I don't need anyone to solve that problem for me, then learn or fit that. So it's a variational calculation on self-generated data from that variational model. And like many of this criticism to machine learning, so how do I know that's correct? So luckily we have variational principle. In this case, lower variational free energy is always better. For example, I can tune my model hyperparameter to get different answers, but I'm always going to trust the one with the lowest variational free energy. So the other thing was those neural networks, often they were thought of as some kind of black box model. How do we make sure we are understanding that model? So here, there are actually two levels of answer. So first of all, I think for variational calculations, the bottom line is I can always don't care about that, because as long as this is sufficiently accurate, predicting all the physical quantities, I don't need to care about what are those neurons or layers we're doing. Except in this particular case of applying such a rational method to interacting electrons in sufficiently low temperature, those models, they do have a physical meaning, because this Boltzmann probability distribution, actually they contain the Landau's energy function. If you take logarithmic of it, you're going to actually say that it actually contains a label of different quantum numbers and their excited energy. By fitting to that, I believe you can extract Landau's Fermi liquid parameters. The other thing was this flow between quasi-particle and electron coordinate. So actually, this is a nice way, like the animation I was showing, it's a nice way to illustrate adiabatic continuity. So you are evolving continuously from quasi-particle coordinate to the electron coordinate. So in that particular case, this is an understandable model, interpretable model. So finally, coming back to connections to tensor network, because this variational free energy framework, certainly it can be used to solve like more closely, these Latin models, which are more closely connected to tensor network approaches. So basically there was like classical distribution. Then because the essence, the flow, what the flow was doing was actually a unitary transformation in the Hilbert space. So suppose you can parameterize a classically tractable unitary tensor network, then do variational calculation on it. You can use this framework to solve quantum systems at finite temperature. So this was actually done in these papers, except that in a general case, we do not have a tractable way to deal with unitary tensor networks, especially in high dimensional, or especially if this tensor network is very deep. So that's why later on, people actually generalize those things to quantum algorithms. Essentially, they just replace the unitary tensor network via a parameterized quantum circuit and perform the same calculation. So I hope this can inspire more progress in along the way of the tensor network calculation for finite temperature systems. Even though at the moment, I do not know how to proceed, except to go into a quantum computer. Okay, that's a summary. So it's a new method for the old problem. There was some new results to be confirmed. And beyond electron gas, I think this can also still be used to do many more systems at a finite temperature. So Xie Hao and Zhang Linfeng were my collaborators. So that's a preprint, that's a code. So thank you very much for your attention.
So thank you very much for great talks. So now this talk is open. Is there any question or comment? Lin-san, please.
Hello. Thanks for the very nice talk. Yeah, nice to meet you again. Just a follow-up question regarding the last few comments that you also make. That I remember, like Gen's group also, like there's a paper about saying that the convex kind of combination of matrix product states can describe kind of finite temperature density metrics very well, or at least they can prove theoretically that's the case. And so I'm just wondering that, and also like given the works that you've done with like using autoaggressive neural network plus quantum circuits, have you guys tried with MPS? And also to me, it's not that straightforward how one can parameterize the MPS parameters, the probability distribution over the MPS parameters. So these are kind of the follow-up question along this line.
Yeah, thanks a lot for that. That's indeed very nice. So basically, you are thinking about those things as MPS, right?
Yes.
Instead of that flow model. So the issue I see was to make sure this, because later on for finite temperature calculations, one of the difficulty was to evaluate entropy of such a density matrix. So very often this requires for the state, they are also normal, because otherwise if you do trace rho log rho, then this is very ugly expression. But that's why at the moment, I'm having difficulty to say, how do I make sure I got a family of orthonormal MPS? Orthogonality might be okay, but normalization might be okay, but how do I make sure they are all orthogonal? Probably it's not that straightforward to me. If that was possible, then I can imagine a way to combine, basically to go further along this direction.
I see. Okay, thanks.
Yeah, no problem. Good to see you.
Okay, any other question or comment? Yeah, Okubo-san, please.
Can I ask a question about using the quantum computer?
Yeah, please.
So you said that to construct the unitary matrix, we can use the quantum circuit. So, but I think at least now, NISQ device, it's not so easy to construct a deep quantum circuit for this purpose. So my question is, how to say, how large quantum computer we need to, how large or how reliable or noiseless quantum computer do we need to apply this method to, for example, calculate effective mass?
Effective mass, okay. So if your purpose was to solving electron, encoding electron system on a quantum computer, I think that's really a long way. That was because it's a fermion with Coulomb interaction, and in continuous space, you need to have the second quantized representation and so on. So that's why through the whole talk, I was using a machine learning. I don't think a quantum computer in reasonable amount of time, let's say 5 or 10 years, can be made for that electron gas calculation. But even so, I think that was not probably the most urgent application of quantum computer, I guess. Okay, coming back to those quantum computer kind of thing, I guess it makes more sense to use them to study thermodynamics of high-dimensional spin systems. Yeah, for high-dimensional, for thermal dynamics of spin systems, I guess we did some experiment with like Ising model and so on. So what we was using was like not so deep. I remember only a few layers was sufficient, because at the finite temperature, you do not need to have actually very deep quantum circuit to at sufficiently high temperature. This should not be very deep. Then in the ground state, this should not be deep either, because basically you are preparing the ground state. So what was difficult, it was like somewhere in between.
I see.
But I do not have more precise number. I think this is something was actual simulation and study. Yeah.
Okay. Thank you very much. Very interesting.
Thanks a lot.
Okay. Any other question or comment? So I have a naive question. You didn't mention about how much computational cost is needed in order to get your result. So
yeah. Okay. So for the largest one, 57 electrons to the for example, those numbers. The whole thing was 8 GPUs in 5 days.
You're using GPU. I see.
Yeah, 8 GPUs in 5 days.
So it's a relatively large computation compared with the usual tensor network simulation in one-dimensional system. But it's okay.
It's comparable, I guess.
Yeah.
The wake time, but yeah. By the way, those diffusion Monte Carlo calculations was from 2013. They were using Jaguar supercomputer. They didn't mention number of CPUs, but I guess it has to be a lot. Otherwise, they won't go to Jaguar thing. Yeah.
So machine learning is much more economic.
Right.
I see. Thank you. So is there any other question or comment? Harada-san, please.
I have a question about the size of systems. Usually, machine learning technique only the finite system can handle. So, if we want to consider about some standard limit size, is it possible to apply the machine learning-like technique for such a thermodynamic case directly?
So yeah, that's a good question. Thanks a lot. So I think here why this was a finite sized calculation was somewhat related to the fact to evaluate the cost function, I need to actually carry out sampling of the electron coordinate and momentum. So this, I think, awardedly pushed me to this finite size calculation. But suppose probably for a different model, I meant different parameterization of those things. Suppose there is a way to directly evaluate that, I mean, analytically in thermodynamic, because this thing was like a trace. The trace was for the whole Hilbert space, or let's say for the whole momentum grid. So if that was possible in an analytical way, then I wouldn't have to go perform finite size calculation. So I guess my answer to your question was that in principle, yes, but I just do not know how to do that at the moment.
I see. Thank you. Thank you for interesting talk.
Thanks. Good to see you.
So any other question or comment?